So in this chapter, we will continue studying light in the form of rays. And when you're studying light as rays, that is called ray optics or geometrical optics. They mean the same thing. So this chapter is a continuation of our study of geometrical optics. And in this chapter, we will focus on how light interacts with different optical instruments. We will only be looking at the most basic and simple optical instruments that you can have, which are lenses and mirrors. Okay, now before we get into the content of this chapter, there are two very, very important concepts that you need to understand. They are real images and virtual images. Okay, so what is a real image? A real image is a point where rays of light actually converge. So what's an example of that? Suppose you have some rays of light coming in from a source. And once again, just to quickly remind you, a ray, what is a ray? You have these plane wavefronts, and rays are just normals that are drawn to the plane wavefronts. So they are just a convenient way for us to visualize the wavefronts without actually having to think of these infinite planes moving along. So remember that rays are just normals to the actual wavefronts. All right, so with that in mind, we have some parallel rays of light coming in. And suppose we pass these rays of light through a lens. A lens is just a piece of glass or plastic which is shaped like this. It's got two curved surfaces. We'll talk about that later on in this chapter. So what a lens does, we'll see later on, is that it makes as the light refracts through the lens, it makes the rays converge at a given point. All right. So this is an optical system. The lens is an optical system which makes light converge at a given point, right? So the point where the light converged is called a real image. So all the light is converging at this point. I've just drawn three rays here, but there's an infinite number of rays. They're all doing the same thing. They're converging at this point. Of course, they don't stop here. They'll continue going. But the real image is the point where all these rays actually converge. So if you put a screen at this point, you will see a bright spot of light there. So a real image can be projected on a screen. All right. So a real image is a point where rays of light converge, and if you put a screen at the location of a real image, you will see a bright spot of light. Okay. Now, what is a virtual image? Virtual images are formed when optical systems make rays of light diverge instead of converge. All right, so to give you an example of that, this is obviously not the only example. We will see that there is another type of lens which is a diverging lens. So that would look like this. You have it's got two curved surfaces, but the curved surfaces are such that are like this. So if you send rays of light into this lens, what's going to happen is they will, as a result of refraction from the lens, they will diverge. They will no longer remain parallel, they will diverge. And as a result of that, yeah, so the rays of light are diverging. Now, suppose you produce these rays backwards. So I'm just using blue to produce these rays backwards. If you produce these rays backwards, then they all seem to be originating from this point F. They appear to be originating from this point F. So this point F is called a virtual image. Notice that the rays are not actually diverging from F, but the lens makes it seem like they're diverging from F. In fact, if these rays are picked up by an eye, the eye will conclude that they started from F, even though they didn't actually start from F. They were parallel rays of light before they hit the lens. So a virtual image is a point where rays of light appear to diverge from. Oops. Virtual image is a point where rays of light appear to diverge from, and obviously a virtual image cannot be projected on a screen because the rays of light are actually not hitting that point. They just appear to diverge from that point. All right, so that's what a real and a virtual image is. Let's start talking about mirrors. And let's start with plane mirrors. Plane mirrors are mirrors that whose surface is plane, not curved. Okay, so a plane mirror is a mirror that has a flat reflecting surface, right? Um, the image that's formed by a plane mirror is upright, identical in size to the object, and as far behind the object as the object is in front of it. We'll establish all these properties in just a little bit. But before we do that, let's just ask ourselves, what is a plane mirror made of? Like, how do you make a mirror? What are mirrors made of? Now, your first instinct might be to say that a mirror is made of glass because all the mirrors that you've seen probably are made of glass. But the glass is really not the most important part of the mirror. All mirrors actually have a reflecting surface behind the glass, which is made of silver. And silver is what does the job of reflecting the light. So, why do all mirrors seem to be made of glass? That is because silver needs to be protected. Silver can, if it's exposed to air, it can tarnish, it can oxidize, and then you have these ugly splotches on it. And so, in order to prevent the silver from tarnishing, it's placed under a slab of glass, and that protects the silver. And that is how mirrors. That's how you construct mirrors. Okay, so how does a mirror form an image? Let's think about that. And then we will try to understand these properties that we just discussed of the um, image. Okay, so I have some animations over here which help you understand it, but I will just go ahead and draw this, and hopefully that will make it clear. So let's say that this is a mirror. So the mirror is perpendicular to the plane of the page. It's a pain to draw a mirror like this. So typically you just draw the edge view of the mirror. So just imagine that there is a mirror over here, but it's perpendicular to the plane of the page, so you can only see the edge of the mirror. All right. Now, if you draw a mirror as a line, then you have to also indicate which side is the reflecting surface of the mirror, or which is the front of the mirror and which is the back of the mirror. So the back of the mirror is indicated by just drawing, oops, so here's our mirror. The back of the mirror is indicated by just drawing some diagonal lines like this. So this indicates that the right side of the mirror is the back of the mirror, and the left side of the mirror is the reflecting part of the mirror. All right. Okay. So let's say that this mirror is placed on the ground, and there is an object somewhere over here. Typically, the object can be anything. It could be a person standing, or it could be your cat, or it could be anything. But typically, when you're making diagrams like this, the object is drawn as an arrow, simply because an arrow has an orientation, right? A size, and it has an orientation. So it's convenient to just use an arrow as your object. So we have an object that's in front of the mirror, and we want to see what the image of this object will be like as a result of reflection of light in the mirror. So let's just try to find the image of the tip of the object, right? Now there's an infinite number of rays coming out of the tip of the object. Let's just pick one. Let me just make the object a little shorter. All right, so there's an infinite number of rays coming out from the tip of the object. Let's just take this ray, just any ray that's coming out of the tip of the object. Now this ray is going to hit the mirror, obey the law of reflection, and it will be reflected like this. Remember that the law of reflection says that the angle of incidence equals the angle of reflection, right? Okay, let's also pick a second ray. So I'll draw the second ray with a different color. Okay, this one. And this will also obey the law of reflection and reflect off like that. All right. So now we have two rays. We've seen how two rays behave after they have reflected off of the mirror. There's an infinite number of rays, as I said, coming from the tip of the object, and they all do the same thing. They hit the mirror and then they reflect off, obeying the law of reflection. Now you can see that. So suppose these two rays are picked up by an eye somewhere over here. Now the eye uh, will not be able to follow the bent path of the rays. Our brains and eyes are not very good at understanding that rays might have changed direction on their way to the eye, and so the eye will simply produce these rays backwards and conclude that they started from over here. So the eye will in fact see the tip of the object over here at this location. And so this you can do the same thing for every other point on the object. And so you conclude that the image of the object is formed behind the mirror somewhere over here. What kind of image is this? Think about that and see if you can answer this question yourself. Is it a real image or a virtual image? The answer is this is a virtual image. Why? Because rays of light are appearing to diverge from here. They are not actually converging there. So this is a plane mirror forms virtual images, and this is a virtual image. And let's also think about um, the properties of this image. Notice that this image is upright, so it's not inverted, it's upright. We'll see some optical systems form inverted images later on. And what about the size of the image? Suppose the image height of the image was hi, and suppose the suppose the height of the object is ho, and suppose the height of the image is hi, right? So this is our object, this is our image. Okay, you can prove from school level geometry, just using similar triangles and congruent triangles and all that stuff, you can prove that HO and HI are the same. So HI is equal to HO, right? Right. There's also another important quantity, that is the object distance, or the distance of the object from the optical system, which is the mirror in this case, and that distance is called DO, object distance. And there is a related quantity, the image distance, which is the distance of the image from the optical system, and that is called di. Once again, you can prove from simple geometry that in this case do is equal to di, right? And so that's really all there is to how images are formed by plane mirrors. And that is why when you look in a mirror, you see a reflection of yourself behind the mirror. Okay, so I, I've got simulation over here, which basically this one just shows you the law of reflection, which you already know. The angle of incidence equals the angle of reflection. This one shows you the same thing that I just mentioned, how an image of an object is formed behind a mirror. You can see that all these rays of light are hitting the mirror, obeying the law of reflection, and if you produce them backwards, you get a virtual image at a point behind the mirror. And this figure is just a nicer version of what I drew. You can see the image of the uh, tip of the object being formed over here, and there is another one here as well, same exact thing, the image of the bottom of the object being formed over here. So so this just shows you how a mirror, a plane mirror, forms an image. All right, now we talked about the object height, which is HO, the object distance DO, image distance di and image height hi, right? The magnification of a image is given by is the ratio of hi divided by ho. So that is the magnification, magnitude of the magnification. So that's the definition of it, right? We'll see later on that the sign of the magnification also has some meaning. So if the magnification is positive, I think I have that over here. If the magnification is positive, then that means the image is upright. And if the magnification is negative, that means the image is upside down. In the case of the plane mirror, the image is upright, so the magnification is positive. And the magnitude of the magnification is simply the ratio of hi divided by ho. We just saw that hi and ho have the same, are exactly the same, and so the magnitude is 1. And so for a plane mirror, the magnification is plus 1, right? So please remember the meaning of the sign of magnification. Plus means it's an upright image, minus means it's an upside down image, and the magnitude of the magnification is just the ratio of the image height to the object height. All right. And we've also seen that for a plane mirror, di is equal to do. All right. Okay. And so that's really all there is to plane mirrors. Okay. The next thing that we are going to talk about is spherical mirror. So a spherical mirror is basically a mirror that is a section or a part of a sphere, right? So if you just if you just look at this diagram over here, you can see that the mirror is part of a sphere. It's a section of a sphere. Now, there could be two types of spherical mirrors. Okay. There could be two types of spherical mirrors. You can have a mirror whose reflecting surface is whose convex surface is reflecting, and that is called a convex mirror. Or you could have a mirror whose concave surface is reflecting, and that is called a concave mirror. Now, what is the convex surface? The convex surface is the surface that bulges out, right? So you can see that this is the convex surface. And what is the concave surface? The concave surface is the surface that caves in. So this surface that caves in is the concave surface. If the convex surface is the reflecting surface, then we call that a convex mirror. And if the concave surface is the reflecting surface, we call that the um, concave mirror. There are just as we can draw a mirror, a plane mirror like this. There is a way of drawing a convex and concave mirrors or spherical mirrors. So you can draw a spherical mirror like this. If the convex surface is reflecting, then you would put these dashes over here. This would mean that the convex surface, or the surface that bulges out, is reflecting. So this would be how you would represent a convex mirror. Convex surface is reflecting. And this is how you would represent a concave mirror. You would draw some dashes on this side, indicating that, so this is a concave mirror. The concave surface is reflecting. Okay. All right. So that's how you can represent convex and concave mirrors in diagrams. All right. So there are some basic definitions here. So since the mirror is part of a sphere and the sphere has a center, the center of the sphere of which the mirror is a part of is called the center of curvature of the mirror, right? So the point C over here. Okay. This line, which is the axis of the mirror, is called the optic axis. Sometimes it's also called the optical axis, same thing. So that's the axis. Uh, the point where the optic axis intersects the mirror is called the vertex of the mirror, right? So you can see this point is the vertex of the mirror. Okay, and the radius of the mirror, which is simply the radius of curvature of the mirror, I mean, which is simply the distance from the center of the mirror to any point on the mirror, uh, is r, this distance. So r is the radius of curvature of the mirror. Okay. Now we will see that a concave mirror focuses incoming parallel rays at a point which is called the focal point. So suppose you have some parallel rays coming in, and they hit a concave mirror. Remember that a concave mirror, the concave surface is reflecting. So what's going to happen to these rays is that after hitting the mirror, each of them will obey the law of reflection. You can see that over here, the topmost ray comes in, and this is the angle of incidence it makes with the normal. This is the angle of reflection. And so after reflection, the ray goes like this. All the other rays also obey the law of reflection, and they come to a focus. They converge at the point F. So the point F is called the focus of the mirror, and the distance of F from the vertex is called the focal length of the mirror, little f. And you can prove with simple geometry, just school level geometry, that the focal length is going to be half of the radius of curvature r. So the radius of curvature is simply the distance of C from any point on the mirror. The focal length is going to be half the radius of curvature. So for a concave mirror, which is also a converging mirror, because it makes the rays of light converge, um, the image is real. Why? Because the rays of light are actually converging at the point F, and so you have a real image at F. For a convex mirror, what happens is after the rays of light hit the mirror, they all obey the law of reflection and then they diverge. You can see that all of these rays on the left side over here in this diagram, all of these rays, on the right side in this diagram, uh, are after reflection, they diverge from the mirror. And so this is a diverging mirror. And if you produce these rays backwards, you find that they appear to diverge from the point capital F. So capital F is a virtual image here, and it's called the focus of the mirror. So it's the point where the rays of light appear to diverge from. And once again, you have the same relationship that the focal length little f is half of the radius of curvature.